All right. Yeah, well, so hello. Thanks for having me over to tell you a little bit about the geology here. And so it's neat when one talks about the geology of somewhere. You have to talk about where the rocks come from and then sort of what happens to them afterwards is sort of the general two-part story to anywhere. You've got all these neat rocks here. And then we've got this whole peninsula that they're up, and we have these cliffs and all of that that we can see them in. So to talk about the first half, to go chronologically, the rocks of Palos Verdes have formed over millions of years. There's some really old rocks, actually, that are the core of the peninsula. They're under our feet right now if we went down far enough. And those are the oldest as well. Those are tens and tens of millions of years old. And so we don't see any of them here where you are. So I won't say much about that. I'll say a little bit more about that if you like back in the clubhouse where I brought some pieces since it's all below ground here. Yeah, something called the Catalina schist.
Right.
It's most of Catalina and it's most of the peninsula too if you count underground. But it only shows up in a little piece of the peninsula. Where we'll actually go in a few months for one of the monthly Palos Verdes Gem and Mineral Society trips that a colleague and I are doing. And so if we gloss over that, then really the story of the peninsula starts around sort of 12 million years ago. And what had happened leading up to that actually is a bunch of land that was out here swung away, and actually that's it right out there. You have a great spot to see this. Usually when I'm talking about this, it's a little farther down and you can't really see it. You have what are called the transverse ranges there, Santa Monica Mountains and then the Santa Ynez Mountains and the northern Channel Islands, all those sort of east-west mountain belts. And those are kind of odd. Most of the mountains around here, around California, run north-south. The Sierras, the Peninsula Ranges, the Coast Ranges, and so on. And really, those were no exception once upon a time. Those used to be here. And so if it weren't for some neat plate tectonic movements around that time, you wouldn't have beachfront property at all. You'd be inland of all of that. But then all of that land sort of swung around, sort of pivoted. The pivot point would be sort of off inland that way, and then all sort of pivoted away off of PV here, and it opened up this whole part of the coast here. So this whole area was stretched out and kind of sank down, and then these rocks started to form in this ocean basin that had opened up here. And between all of this. And so, Catalina would have basically just been part of the coast, part of Orange County coast, and those mountains would have been here. They pulled away.
Were they mountains when they were here, or was it flat?
Oh, it's a good question. It wouldn't have been those mountains yet. Those have been pushed up by some different faults, but there was some topography there. And in fact, it's neat. You can go, if you go down to some of the beaches in Orange County, like what is it? Santa Onofre State Beach, I think is the best one. And you see these rocks, and there's these big boulders of that old rock I was just mentioning, Catalina schist. And if you actually look at there's little indicators, you can tell which way those boulders were coming based on some of the patterns. A flowing stream or a moving mud flow will leave little kind of indicators of the direction of flow, just like ripples can tell you, in a river, which way a river goes. And all of that was coming from the west. And so you actually say, whoa, there must have been some really steep, rugged landscape that was dumping all of these boulders. But then you turn and it's just the ocean, and that's all sort of gone now. So there would have been some rugged topography, but that's enough millions of years ago. It wouldn't have been this. That's too long ago for the landscape to match. So you have to dismiss the notion of, there was no PV Peninsula, there weren't those modern mountains yet. But some of those same rocks that are pushed up there now existed, and that's where a lot of this evidence comes from. There's all kinds of things in the rock that are sort of 90 degrees off now, little like frozen compass needles and little channels indicating which way things were flowing out to sea. And they're all 90 degrees different from there, from everything along here, because, you know, when you put them back, they all sort of match up. So anyway, this all opened up, and this was this big ocean. And then things started to settle out in the bottom of the ocean, mostly mud that would gradually settle out of the water. It takes a long time, accumulates rather slowly. And that mud became what's called the Altamira Shale. And the Altamira Shale is the main rock of the Palos Verdes Peninsula. And it's what you have really going this way, you know, and all into Malaga Cove and all of that is the Altamira Shale. It's very broadly part of something called the Monterey Formation, which is a very broad term. Someone would say too broad. But there are all of these ocean muds of the same age as our Altamira Shale, all on the coast, and all in the Central Valley too, actually, because when we go back, this is about 12 million years ago we're talking, and 12 million years ago the Central Valley was an ocean bay. And that's, you know, there were sharks swimming in what's now like Bakersfield, and there's actually some great places you can go and find like shark tooth fossils and megalodon fossils and stuff even, because that was all this ocean. And it was a really prolific ocean in terms of what was living in it. You had all of this upwelling, cold, nutrient-rich water upwelling on the coast. And so there was a ton of like plankton thriving in the ocean there. And then at the same time, because you had these little sort of constrained little basins here, and some you can still kind of see today, if you look at the seafloor, there's some of this kind of undulating back and forth kind of pattern. You got these things that were cut off enough from the main ocean that things wouldn't decay as readily. You would get what are called anoxic conditions, anoxic without oxygen. So the deep bottom of the seafloor, there wasn't enough of the oxygen there that you need to actually break down living things when they die. And so this plankton would die and it would settle down kind of into the mud at the seafloor. And because it wouldn't all decay, it would get buried. Even the organic parts would get buried. And that turned eventually into oil. So actually all of California's oil wealth comes from primarily the Monterey Formation. And that's why the Central Valley is such a prolific oil region. Like Bakersfield is the oil capital of California, and it's that same stuff. But also we have a ton, you know, in the Long Beach oil field, the Signal Hill oil field, the Torrance oil field, the Wilmington oil field, you know, basically everywhere but here. And so
by an oil company one time?
the peninsula, you mean?
Right here.
Oh, this would have been all, and I think even, you know, big derricks all on the beach. I know there's photos of like Wilmington and stuff where it's like right up to the water, and you can see people in the 20s kind of like flappers era bathing suits having a beach day, and there's just like a forest of oil derricks behind them. Yeah, and it would have been all up in here too. Yeah, pretty much everywhere but right here. And so that's that oil, is that broken down and kind of buried and cooked soft part of all those things that were living in this ocean and getting buried in this mud, the mud which has all been compacted into this thing, the Altamira Shale, which is that sort of, you know, tan, kind of crumbly, breaks in those nice sort of sheets, and those sheets are the original layers that would have formed on the ocean floor. So that's the original layer, and they're used a lot for, you know, paving stones and stuff on the peninsula. And so that's the Altamira Shale, about 12 million years old. And so that formed then, and that what would go on to become the oil formed then. And then what's interesting is that PV is so different and special geologically from everything around it, but not yet, not 12 million years ago. At that time, this was part of the same ocean that all of that other stuff was. And it's really the fact that this got pushed up to make a peninsula that makes it special today. So actually, if you go over there to Redondo Beach, or if you go over to Torrance, or if you go past, I'm over in Pedro, you go past that to like Long Beach, it's actually all these same rocks. Altamira Shale, you know, with Catalina schist down beneath it. It just hasn't been pushed up into a peninsula. So it's still below ground and you don't see it. It's buried by some younger things that have covered it up. and that's actually sort of kept the oil safe down in the ground. And so that's why you see all those oil fields. In fact, so here's a geologic map of the peninsula. And so here's our PV Peninsula. You know, there's the harbor. You're right here on the sort of northwestern extremity, right before things go into this rather straight kind of redondo beach neck of the woods. And then here's Torrance and so on. And all the colors indicate different rock types. And we can look at this up close, not to worry, and I'll bring it, you know, when we go to the clubhouse too. That little bit of blue is that Catalina schist. There's over by like George F. Canyon Preserve, if you're familiar. If you do a hike up to there, okay.
Where PV Drive East.
Meets PV Drive East, meets PV Drive North.
Bill said curator, mother hen of that.
Oh.
I don't know what her title is.
Wonderful. Yeah, well, she does great work. Yeah, whatever the title is. It's a lovely place over there.
See it when you walk through the canyon?
You have to go up, basically. If you follow the trail, takes you up to the top. And you get up in there, and there's just a few little exposures. It's the one way without a boat you can go see the Catalina schist. It's that one little area. So that's this blue. But it's underneath all of this. That's just the one little place it pokes up.
Yeah.
And then all of these oranges, that's that Altamira shale, some of the different units of that. But it's all out here too. And what's interesting actually is this map is covered with these little open black circles you can maybe see just plastered everywhere. Little open black circles.
Yes, yes.
Every one of those is an oil or a gas well. Yeah, and there's more too. This map is outdated. And I mean, you can see like over here, the Wilmington oil field. It's like a couple of block or something. What's that?
Shouldn't the old map have more oil wells?
Oh, that's true. Yeah, they're not all active anymore. Yeah, and in fact,
They're not like still drilling.
Oh yeah, quite a bit actually. So that's better not say too much about that just because I don't want to get too off track, but it's fascinating actually. Most of the oil is gone now here. We had pound for pound maybe the best oil rocks in the world. It's not as much of it as like if you look at some of the huge oil fields in the Middle East, the extent of those, you know, the square mileage and everything dwarfs what we have here in California. So it's more oil. But if you take the same volume of it, the amount of oil in these rocks, in the Altamira Shale is almost, unparalleled worldwide. And that's why it's been such a big, rich oil place for over a century now. And it is largely tapped, but it's still working. And so there's a lot of the world's major urban oil fields are primarily here in LA. They've managed to keep going despite the urbanization. And because people don't care for that sort of thing too much, it's hidden to sort of various extents. You know, not like hidden like call the authorities, you know, it's all like above ground, but just, to not sort of people don't want to see big pump jacks or the like. So, like.
I think there's some community that just decided to move on to the LA Boulevard.
Did they really? I hadn't heard about that. I could believe it though.
Yeah, just recently, like a month ago.
Yeah,
Yeah,
exactly.
yeah, I
Wow.
don't remember. I think it's.
I think it was around the La Brea tar pits. Maybe.
Even the one by the Beverly Hills High School. Yes.
Yeah, they took down the tower. Yeah, but it's true. Yeah, and it's interesting too. The a lot of communities are talking about that sort of thing, and one of the things to make it higher stakes is that some of these oil fields, as they sort of dry up and you're not able to pump anymore, you've recovered most of the traditionally or the conventionally recoverable oil. So then what's left is the harder to recover oil, which is potentially recoverable if you do things like fracking. And so that's one of the reasons, that there's renewed discussion of these oil fields, is some of them are getting to the point where it's, is it time to sort of let the field die, or is it time to, do some of these other techniques? And so, Baldwin Hills oil field is one of the big places that's been discussed. And it's tricky. The community there has been looking forward to that oil field ending its life and turning that whole thing into like a huge public park sort of area. But because of some of these different techniques, I don't think they're fracking over there. But there are some other things you can do.
I have a friend who lives over there that did frack in there, and it was causing tremors.
And they were getting really, that's...
So they had to stop I don't know, they may be trying to figure out a new method or something.
Could be. I don't know too much about the field
Yeah,
in
but
particular,
they
but
were
that's
doing it there,
wow.
at the height of it before the Middle East dropped it, whatever. Anyway,
Sure, that's
but it absolutely
and they
caused
could
traffic.
feel the wow.
Absolutely.
That's interesting. And there's other things you can do, like pumping steam underground can sort of heat up the thick stuff and get it to flow, and that doesn't pose the same hazards typically, though pumping a bunch of fluid into the ground, you still have to be careful. That can, if you do it wrong, can generate some earthquakes too. So anyway, it's an interesting time for urban geology, or for urban oil fields. The Baldwin Hills oil field, that's the biggest sort of conventional urban oil field where it's just a big hill, pump jacks, you drive right by and see it. But then there's other ones, like someone mentioned Beverly Hills High School. That's an active oil field, and they're still pumping, and they were still drilling until maybe 5 or 10 years ago. I don't know if you know the Tower of Hope. Beverly Hills High School had that. You can still find photos online. This big, weird tower full of paintings that children had done. So that tower was to encase and hide the actual drilling operation. Because what we think of, the big wooden kind of derrick built up and the oil spurts out the top and, yeehaw kind of thing. Well, so for one, they don't make them like that anymore out of wood. It's a metal tower and it doesn't need the big bracing. But for the other, that's actually a drilling rig, is what that is. Once you've actually drilled the well, you don't need that big tall thing to pump. You need one of those pump jacks you've maybe seen that kind of goes up and down. Or if you really can't have that, if space is a concern or the view, there's even slightly more expensive ones you can put that can be entirely in ground. There's some of those, like as you go over to Long Beach, kind of beneath some of the bridges, and it's just a little sort of panel, and there's a pump under there, pumping. But the towers are tall, so those are harder to hide, but people have done it. So like Tower of Hope, or there's a whole big building, it looks like, is that a church maybe? It has this sort of ornate tower in kind of that same, like along Wilshire, as an oil field, and there's a building with no roof on it. You can see like on Google Earth, the satellite view, you can look right into the building, and it's all an oil field and so on. And actually,
Columns on the islands off of Santa Barbara.
that's off of Santa Barbara, they have some offshore like drilling platforms. Yeah, we actually have them just offshore in Long Beach too. Do you know those little like resort islands that you see out in Long Beach? If you've ever wondered what those are artificial islands for oil. And they have the little tower on them. And again, that's the drill rig that drills, and it's hidden. And then it's actually, you'll see, if you pay close attention, you'll see it move. It's actually on these like railroad tracks. And it goes around and drills wells and then moves, and then they start pumping at each one that's been drilled. And modern technology, you can drill, you don't have to just go vertical. So they actually go down and then way out into the surroundings so that they don't have to plaster it with derricks like in the old photos. So anyway, a lot of interesting oil. Better stop talking about oil, but a lot of interesting oil around here.
Unless there's some here, we're not interested.
That's right. Well, and there really isn't any here, actually, even though these are the same rocks, because these rocks have been pushed up and the oil is leaked out and it's gone for the most part. You'll still see, though, little bits of tar sometimes along the beach, and you might think, oh no, was there an oil spill off the coast or something? And, sometimes, like there was that one down by Long Beach or by Huntington, a little while ago. But actually, most of the time what you're seeing is the natural tar seeping out of the Altamira Shale. The same tar that we're still below ground is feeding all of those local oil fields. So that's the Altamira Shale about 12 million years ago. And then that's capped by something called the Valmonte diatomite. And you've got a lot of that right here. You're kind of right at the boundary between that older Altamira Shale and then that Valmonte diatomite. And that's that really white, light, crumbly rock. And in fact, where was the rock fall? Is that like right over here? Or just over, okay. And you can go right up, on the beach. I remember before I ever met Dan or had ever been here, I had been down there with a geology class from El Camino, and that's one of the things we looked at, is where some of that white rock is all crumbled and tumbled down the hill. And one of the things I would do is I would tell them, I'd go up and I'd and I'd pick up a big boulder and they would all, right? Because it's remarkably light. It's maybe, half or less what you would expect a rock to weigh for whatever given size it is. If you haven't tried it, I highly encourage, you don't need to do the big one. Don't hurt yourself. But like if you pick up a fist-sized piece of that really white crumbly rock and kind of heft it, you'll be shocked if you haven't done it, how light it is for a rock.
And they float on money and hawthorn, right? That to make it very fine.
Oh, I'll bet they did because...
That's what that big pit is. It's all sides to make it good.
Which pit is that?
That hawthorn and Via Belmonte?
Oh, that's why they call it Belmont.
Yeah.
The Valmonte diamite, that makes sense. Let's see, that's probably even marked on here as a quarry or something. Oh, Valmonte. And hawthorn. Oh yeah, there's even a little, very cool. Yeah.
Does that rock flow on water? Is it that light?
No, pumice is the only rock that typically floats on water. Diatomite is generally not quite light enough, and also it'll soak up water almost instantly because it's kind of powdery, and that'll add to its weight. And so maybe you could get a piece to float momentarily, but then it would sink. Yeah, pumice is the one that's full of little bubbles. It's a volcanic rock, and it's bubbling as it oozes out, and it solidifies so quickly it freezes and traps the bubbles in it. Like if you've ever had a carbonated beverage explode in the freezer, and you end up with that weird frothy ice, It's that, except instead of water freezing, it's lava freezing. So that's pumice. The diatomite is kind of similar, though. It's so light because it has little bits of air trapped in it, too. But instead of bubbles that formed from a lava, the Valmonte diatomite, it's a sedimentary rock. It formed at the bottom of the ocean floor, just like the Altamira shale. But at a time when those plankton that were thriving out here and making all that oil, were especially prolific. And so it kind of dwarfed the amount of mud that was slowly settling out of the water, was dwarfed by all the plankton that were living, blooming, and then dying. And they would settle down to the ocean floor, and that organic matter would become the oil. But the plankton, it's not just organic matter. It's not just these little single-celled plankton things. They actually precipitate a little shell, a microscopic shell that goes around their single cell. And that doesn't decay because it's not organic. It's made out of calcium carbonate, the same thing that big, seashells are made out of. Oh, you mean like the bioluminescence? Yeah. No, that's part of the soft part. That's, I think, some kind of neat protein, I think, though that's outside of my specialty, yeah. So you have these little calcium carbonate shells. And in fact, chalk is a natural rock. Chalk is basically diatomite, but it's made out of calcium carbonate, which most seashells are made out of. So what we have here is diatomite. It's very chalky. It's the same kind of thing, except the little shells, instead of being made out of calcium carbonate, they're made out of silica. And so that makes the properties a little different, and they're useful for different things. So like chalk can be used as a natural antacid because the calcium carbonate reacts to acid. The diatomite, you wouldn't want to take that for an upset stomach. But you can use it for other things. So someone mentioned being quarried to make diatomaceous earth. And so this crumbly stuff, when you break it all up back into this loose powder, you get diatomaceous earth, which can be treated to make filtration systems. A lot of the higher end pool filters are diatomaceous earth. And so all those little tiny little shells, the water having to pass through that fine stuff, it does a better job than like sand is a sort of a cheaper pool filter material, but it's not as fine. And then it's also used like in cat litter. And believe it or not, we eat diatomaceous earth pretty much every day because it's also these tiny little sharp silica bits are sharp on the microscopic level, so it doesn't bother us. but an insect can actually get kind of sliced open by one of those. It can make enough of an incision to kill the insect. And so diatomaceous earth is used as a natural insecticide. You know, it's non-toxic. You don't want to breathe it in. You don't want a lot of silica dust in your lungs. So don't go just, you know, throwing it everywhere. But like, it's not poisonous. It doesn't, you can eat diatomaceous earth and be fine. You just don't want to breathe it in. So actually granaries will put diatomaceous earth in with the grain to discourage insects from coming and eating it all. And I went on a little crusade against some silverfish. It's so humid around here that we're trying to move in. And that was my big weapon, was diatomaceous earth. And so anyway, yeah, a lot of uses that has. And a lot of the Altamira shale was made of similar stuff, but it was buried deeper and compacted. And that silica actually recrystallized into, instead of all these little microscopic shells, into this solid layer of silica, or like chert. And so there's some of the layers of the Altamira shale are very cherty, and you'll see it's not tool quality. Chert is used sometimes to make arrowheads and stuff traditionally. Chert and obsidian are the two big rocks that are used or have been used through time to make stone tools. And it's not quite that quality, but you'll see the same kind of jagged, slightly glassy edges almost and stuff. But the Valmonte diatomite here, it wasn't buried as deeply, it didn't recrystallize, and it's still that kind of loose, powdery material. And it's so light because all of those little microscopic seashells are empty or hollow now, right? And under a microscope, you know, it's kind of this dull, kind of off-white, boring rock. Under the microscope, it's fascinating. It's all these ornate little shells. And that also then, though, makes it so crumbly, because it's this sort of loose-ish, you know, not too compacted together and light, kind of soft thing, which is part of why there was that rock fall made out of that right down there. What's that?
Are rock falls?
I might be.
Other side of that point right there.
Of that point.
Yeah, it's
There's
all
one
okay.
over here too, though, right? Maybe not on your property, but just a little. I think that's the one I've actually been to, but same idea. And in fact, really just about the same rocks, as I'll tell you about in just a moment. And and then mixed in, not right here, but there's some volcanic rocks too that have at the same time, because everything was pulling apart as that mud was settling, you get little lava flows. So a lot of the headlands further down the peninsula are there because of that hard, solid, black volcanic rock basalt, like in Hawaii, which resists the ocean waves a lot better than that kind of muddy Altamira shale does. So that's basically where your rocks came from. Do you have any questions about your rocks?
Volcanoes up in that?
Yeah.
They were all over California. basically.
Yeah, there would have been, and a lot of this was erupting underwater, so it wouldn't be like a big, Mount St. Helens kind of volcano, but still active erupting
Our
volcanoes.
mountains, even though they're
Yeah.
caused by tectonics, they're also volcanoes contributed to the.
Some of them, yeah, it depends on the mountains. Like the Sierras is all an old volcanic belt, and all the volcanoes have eroded away, and we're seeing the deep roots now. And yeah, there was volcanism out here as well, mostly underwater. And you still see remnants of it, like the hot springs over at White Point, that are still there. And before an earthquake kind of shifted things, was actually part of a hot springs resort. That's that same heat underground that's left over from some of that hot lava that never came to the surface. Yeah. Oh yeah, so that's a nice big piece of Altamira shale right there.
Altamira shale, PV stone is Altamira shale.
Yeah, I heard the term PV stone for the first time recently, but like that's there's not a lot of limestone on the peninsula here. There can be kind of similar in some ways, though. You know, they're both formed in the ocean, and they'll have little fossils in them and stuff. And there's different layers within it, which is
Very heavy.
Very heavy. Very dense.
interesting. And that might be because there's different things you'll find in some of these different layers. Some of them are more silica rich, like I mentioned, kind of cherty.
Only found here pretty much.
Interesting.
What are all the fireplaces made out of?
So
in
that's
the track hole.
that's Altamira shale. That's the old stone. Like we have Altamira shale, but there's these different layers within it, and I don't know if certain ones are specifically used more for the building, because there's the silica-rich ones, there's phosphate-rich ones, and if it's really heavy, it might be. We have a lot of barite. I brought some actually, a mineral called barite that's remarkably dense, kind of the opposite of diatomite. And so if you have one that's got kind of some extra heft to it, that might be a lot of barite in there.
All of it that's been used is there. Very,
That's
Interesting.
White. You can tell it's kind of white, and there's a lot of stone that are kind of gray. So,
Right, that's
Shale
all
like.
great.
brown in it.
it's got brown in it, but there's a lot of white. I don't know what.
I'll bet there's a certain, because they've even been mapped out, and you can see like the different oranges on here. You know, there's the lower Altamira and the middle, and there's these notable differences in the details. It's all ocean floor, you know, settling out, but what all it's composed of varies. Oh, wayfarers, yeah, built out of those nice big slabs of the, yeah.
It's all the same.
That's all good.
That's Altamira shale, yeah, and it might be one of the specific layers that's, you know, it might be better to build out of the more this or the more that one, I'm not sure. But yeah, that's all local. And there used to be some big quarries on the peninsula, and they locally source all of that, yeah.
Is this oil a product of the organic vegetable matter or animal matter also?
Well, so it's mainly plankton, which are these single-celled things. So they're not really plants or animals exactly, but they're sort of analogous to both, actually. And so there's these terms phytoplankton and zooplankton, and phyto is the same as like kind of like photosynthesis and kind of that root, and so that's kind of the like the plant plankton, and so that forms the base of the food tree in the ocean, just as plants do on land. And then zooplankton or zooplankton, it's the same root as in like the word zoo or zoologist, means animal. So those are sort of the animal-like plankton. Those are the ones that actually run around and eat the plant-like kind of plankton. And yeah, well, it's yeah, the web of life and all that. And so you have kind of equivalents of both. And so the what we have, the diatomite here, diatoms are photoplankton, and so they're that kind of primary producer. Yeah. Yeah.
Wow. This structure comes right down and like a big sand line or something.
It is. Yeah.
And is that associated with any kind of fault line?
Not especially. Yeah. So right. So let me tell you now that we know how we got all these rocks, but last time we left them, they were all at the bottom of the ocean, and now they're decidedly not. Yeah. So part two. Not the formation, but the deformation or the changing of all of this that gets you what we have today. So this whole peninsula has been pushed up along the Palos Verdes fault, or the Palos Verdes thrust. And so that is this dotted line. Dotted actually is a symbol that means it's buried, so you can't go and see some dramatic, you know, crack or anything. But next time it goes, you know, at least for a brief time, there will be a little rupture you'll be able to see, yeah, on the ground. And you might notice it goes almost, yeah, and it goes almost right at the boundary of where all these colorful, color-coded rocks are versus sort of the boring nothing here. And that's no coincidence. It's the south side of that fault that's being pushed up and actually kind of up on top of or over this stuff out here. And so that's what's brought up all these older, deeper rocks on the peninsula for us to see. It's all the same rocks out here, but they're still buried. And that's also what's built up our topography here, the peninsula that stands tall as these hills, whereas all of this is flat and was actually still ocean until only some tens of thousands of years ago. Eventually this filled in between us and sort of the mountains towards LA was this ocean basin that just gradually filled in with mud and sand and stuff. So that fault is pushing all of this up, and it's active. It's mostly what's called a strike-slip fault, which is the same. You might know about the San Andreas. That's our big fault here. And that's, you know, the big one. When we have the big one, that'll be on the San Andreas. Hasn't happened until 1850 something. Since 1850 something, even things like Northridge, pretty big, was a smaller related fault. And so nobody has experienced a fault on the San Andreas in Southern California that's alive today.
For what that 1857 was?
Yeah, they have a pretty good idea of the magnitude. I think it was about a 7.1.
Oh, okay, so it was really,
So
they say it can't get over 7. It's not going to be like an 8.5. Like
it wouldn't be quite that high, yeah, because we don't have the right tectonic setting for the biggest earthquakes of all time. We actually used to. Back when the Catalina schist formed, we had where two plates come together, which is like, yeah, that's, this peninsula has everything, yeah. So that's like Chile actually has the biggest earthquake ever recorded because they have that. The Pacific Ocean is being pushed down under Chile. Alaska comes close to the record, and there's also same thing is happening up there, and that's why they have active volcanoes are fed by things getting pushed down and melting. So we used to have that, don't have it anymore. So we'll never have like a magnitude 9 or anything. But what we could get, a 6.7, a 7, a 7.1, a 7.3, is still plenty, you know, yeah, to be a concern. So there's a lot of earthquake prep.
It's just that one fault that's created the peninsula?
Yes, and
That's pushed the whole thing up.
that's pushed the
all
whole
by
thing up.
itself.
Yeah,
Wow.
because, yeah, and you, yeah.
I read a book about the geology here, and they're talking about the 3 dockings.
Okay.
We use the word dockings for the 3 levels in main levels that you see in, in silhouette of TV.
Uh-huh.
How does that fit in, or is that nonsense?
No, it's a great question. Yeah. Yeah, so this whole thing is pushed up, and some people seemed a little surprised. This whole peninsula along one fault, but if you look at the San Andreas, there are things, that was actually my research, was I would look at some things, and then I would drive about 150 miles, and then I would go look at the same things on the other side of the fault. Things had moved laterally, you know, about 150, 200 miles even in places. And then the San Gabriel Mountains, the San Bernardino Mountains, that's all been pushed up along the San Andreas Fault. So that's all because that fault is there. And it's specifically, the San Andreas is mostly one side sliding past the other. We're actually headed for San Francisco. If things keep up, we've got about 25 million years until Dodgers-Giants rivalry becomes a crosstown rivalry once again, because we would sort of come to rest right next to San Francisco. So it's mainly this sort of one sliding past the other thing. But if that fault isn't perfectly straight, if it makes a little bend, then where it makes that little bend, then locally where the bend is, the two sides that are mostly just sliding past each other are getting rammed into one another. Or pulled apart, depending on which way it bends. And we have both in California. The Salton Sea is below sea level, is a place where it bends one way, and the two are pulling away from each other and sort of opening up a gap or a hole. San Gabriel Mountains, it goes the other way, and up they go. And so we have the same kind of bend. We have out here at sea is this fault, and there's no peninsula because things are just sort of sliding one past the other. And then as it comes on land here, it curves around to the left or bends around. And that's what causes locally out here, things are just sliding to the northwest. But where this bend is, now they're sliding northwest into that bend or against that bend and getting pushed up. And then it goes back out to sea and sort of straightens out again. This fault is not as big a deal as the San Andreas fault, excuse me. And so the Palos Verdes Peninsula is not as tall as the San Gabriel Mountains, and this fault doesn't go as often. It's every few or even several hundred years, I forget exactly how many, as opposed to about every 100 to 150 on the San Andreas. But it's the same kind of thing, and it pushes all this up.
How far is that fault from where we are?
Not far, because you have the dubious privilege.
10 miles?
You have the dubious privilege of living at the northwestern end of the peninsula. So see all of that flat land out there? So that's flat because that's on the side that isn't going up. And right at the base of the hill, right where things go up, that's the fault. So you're right here. The fault is here. And let's see, we've got a scale bar here. So that's a half mile. You might be a half mile even from it. Yeah. So, yeah.
Earthquake insurance.
And when was the last time you saw it?
Oh, offshore?
Yeah.
It's roughly along there. Actually, I wonder if that's related, come to think of it. Yeah. It's sort of right, let's see, what have we got
Half a
there?
mile, that's it.
About a half a mile.
Oh,
Yeah.
goodness.
It's south of PCH here. And it's sort of like, let's see, what's the cross street here? Miramar? Miramar? Is that sort of right about right there?
Oh, my goodness. We're debating about earthquake insurance.
Sure, sure. Yo. Yeah, and that's tricky. You know, California, lovely place, but it certainly does have its faults, and so that's something to consider. Yep. And so being proximity to a fault can matter. So can what you're built on makes a big difference. And actually, in some ways, it's nice being on the peninsula. We're on this kind of solid rock, and so that tends to fare better than if you're on sort of the loose, like out there are some old sand dunes and stuff that are much looser and can shake more. And so it's sort of better to be on the solid rock. Though, of course, one has to be careful being right on, you know, the edge of the solid rock. There's concerns there. And so, in fact, in general, off the peninsula, the big hazard associated, besides just shaking and toppling, is liquefaction, the ground sort of liquefying. That won't happen here on the peninsula, but on the peninsula, the big hazard is landslides sort of shaken loose during an earthquake. And there's hazard maps, actually, that the state has even that have mapped out areas of particular hazard for those. So this all got pushed up, but it didn't just come straight up. It kind of, as it got pushed up this fault, the fault dips towards us, so it's about a half mile that way, but it's also sort of down there, right? Because it comes down at an angle beneath us, and the whole peninsula is sort of sliding up like a ramp almost in that direction. And so as this pushes up and slides up this ramp, it gets kind of like crumpled or folded like this too. We don't usually think of solid rock as folding, but given geologic amounts of time and on a large enough scale, it does. And so all those originally flat layers have been warped up into this, what is called an anticline. And, oh, that's a great question. I don't know, but it's slow. The San Andreas can go as fast as like 25 millimeters a year, or like about an inch a year. The PV fault is way smaller. It's got to be somewhere in the like maybe few millimeters a year on average or something, you know, like maybe 1/10 of an inch-ish, very, very broad sort of guess. It's known, I just don't know. We could look it up, actually. There's some great online, there's some good maps that'll show you that. So this whole thing has been folded, which is actually why, in general, the rocks on this northern edge of the peninsula sort of slope north, and the rocks along the southern coast of the peninsula tend to slope south, as you're seeing the two sides of that big fold. Yeah, and that's pushed it up. It's folded and it's pushed up, and as it's pushed up, that takes the old beach and it pushes the beach up as well. So you can see out there, here you've got this nice sort of broad sandy beach, but looking just right in there even where it's rocky, you've got this wave cut platform kind of just below the low tide level. You know, at a very low tide, even if it's still water, you could walk out for this long distance on basically a flat surface, you know, and just be in sort of knee-deep water or something. And that's there because all the rock that used to be above that has been carved away by the ocean, by the waves. They've cut that down to about the low tide level, or just below. It's called a wave-cut terrace, and it's this neat kind of oceanographic phenomenon or feature you find. So what's interesting, though, is imagine, you know, we have an earthquake on the Palos Verdes fault and everything pushes up, then that terrace is going to come up a little bit, you know? And then the waves will cut it back down, but it'll come up a little bit. And if there's a chance for sea level to drop, for it to come up pretty rapidly, or for sea level to drop, like during an ice age, for instance. When there's more water on land as ice, it leaves less in the ocean. So like during the last ice age, a lot of what's just offshore of the port of Los Angeles was all dry land, actually, and people would have been living, you know, potentially even, or actually, I got to be careful with here. I'm not sure exactly when people arrived here, but certainly other places, like a lot of the really old archaeological sites in Europe are underwater now because the old coast, you know, was farther out. So if we had something like that, if we had another ice age and sea level kind of dropped, that would expose that terrace. And then there'd be an earthquake, you know, and then a few centuries later, another earthquake, and it'd go up a little more. And eventually, you know, by the time the ice age ended, say, and water level came back up, that old terrace would now be kind of uplifted so much it'd be sort of stranded up above. And there's actually 13 of those, 13 marine terraces, they're called, in Palos Verdes. And so those were those sort of, I think you call them dockings, someone said? Yeah.
Yeah, that's the book that I'm talking about. Those are the dockings.
The dockings, those are all the old beaches. And so it's almost like a conveyor belt. You form a beach out there, and then you push it up. And that's why the peninsula is so terraced. There are some great places to see it. Not right here. You're kind of right up on the northern end of it. But as you go out there, there's some places where you can look and really see flat, and then step up, flat, and then they go up, flat. Every one of those is an old beach. And the higher you go, the older they are, because it's taken longer for them to have been pushed up. You know, the one on top of the peninsula was pushed up first, and then the next one formed, and they went up together, and then the next. So you sort of step back through time as you step up those terraces. And paleontologists have done just that, and gone and looked at the fossils of each of these terraces, and each one has progressively older fossils. It's also why on some of those terraces, we have these nice solid cliffs made of solid rock, but right on the top of the terrace, sometimes you'll dig down and you'll find rounded beach boulders, and with all the little borings in them, you know, from the gastropods that were living in them and all of that. And you'll think, what is this doing here? And that's actually because that's that old beach. Like, I'm right by White Point Royal Palms Beach, and there's that nice ramp down. And so everything up top is so flat, it almost looks like they paved like that, or leveled, you know. That's actually just, that's the youngest marine terrace, yeah. And then there's more above that. And as you start going down that ramp, if you ever go there, next time you go down that ramp, just kind of look to your right, because the ocean, the big view, is off to your left. But look to your right, and it's all this solid rock, and then right at the top, you'll see all these rounded rocks full of holes. That looks just like the rocks you'll find once you get down the ramp at the beach, and it's the same thing, it's just a little older. So this has all come up, and I've got in the clubhouse there, a little map that shows the terraces. So this whole thing has come up, it's folded, these terraces have been uplifted, stranding these fossils there. And then what's interesting too, is that landslides are common on the peninsulas. Everything gets uplifted, and as the ocean cuts in, and you'll notice though, interestingly, here in this sort of very light tan color are a lot of landslides. Here's the big Portuguese Bend landslide, right? That creeping segment that makes that road so expensive and all the utilities are above ground. It's actually only part of a larger ancient landslide complex that was reactivated due to human activity, as I was talking about the other weekend actually at a little talk. Big complex. Here's another one, South Shores. This map is too old to show the 2011 White Point landslide. You probably remember that dramatic, yeah. And then, you know, Sunken City by Point Furman is over here. So you'll notice landslide, 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 landslide. No landslides to speak of over here. And that's actually because of this anticline, these layers all folded up. So all on the south part of the peninsula, these layers dip south. And so the layers are already sloping out to sea. And so when the waves come in and cut away the cliff, those layers can just sort of almost fall out of the cliff and slide right down those natural layers. On the west side of the peninsula, things are sloping either south or north, but the waves cut in from the west. And so those rocks don't have the same nice surfaces to sort of fall out of the cliff. And there are almost no landslides on the west side of the peninsula. And you have the dubious honor of living one of the few exceptions. You've got this bowl here that formed due to a landslide. And that's because as you get right near this fault, there's this major anticline, but then there's a little bit of kind of back and forth folding right up against the fault. And there's lots of these little traces mapped on here, happy to show you if you're interested, that mark where the layers change from dipping one way, dipping another, dipping one way, dipping another. And you live right on a little syncline, they're called, which is the exact opposite of an anticline. Anticline goes like this, kind of an A shape. Syncline goes like this, kind of a U shape. And so you're in a U. So, you know, you mentioned, oh, diatomite rockfall over there. And I was like, oh, wait, isn't there one right over here? Well, it makes sense because it's actually the same rocks that are there, slope this way, and then they go kind of down under us, and they come right back up over there. And you can see actually in the bare rock exposed right there, you can see it kind of sloping towards us. That's that original flat layering. It's now sloping towards us. And we can't really see a great surface right in here, but over here, it's sort of sloping towards us as well. So opposite directions. And there's this sort of trough in between. And the trough, that's exactly what you've got. And it's not a level trough like this. The trough kind of tilts this way out to sea. And so that allowed what was in the center of that kind of sloping trough to sort of slide right out into the ocean at some point, which is what's opened up this lovely sort of bowl here as opposed to the more sheer cliffs you see other places. The Portuguese Bend landslide is also kind of a big, broad syncline, a much larger scale kind of thing. But the same thing, it's fairly common where you have a little trough like that. It can allow the center to sort of slide down. And this continues to go up. And actually, as you go this way even, and you start to drop down where things have been uplifted very little, there's not a full marine terrace, but there's something called the San Pedro Sand, just kind of right along the coast there, which is much younger, kind of ice age ocean deposits with younger fossils in there. So you're at a very geologically interesting place where sort of the Altamira shale is capped by this diatomite and folded into this syncline with these younger fossil-bearing rocks right over there, and this landslide in the core of this little fold right here. So kind of a whole lot going on, and kind of, you know, an ideal field trip location, really. You can kind of see it all almost in a sense of what you have at the peninsula. So that's how this all came to be. And thanks for listening all about it. And I'll mention, by the way, also, so I'm starting to learn a little bit more about biology now, just in an amateur sort of way. And so when I met Dan, and we hiked around a little bit to look at the geology, we ended up talking more about plants than we did about rocks, though we did both. And he was nice. Yeah, he was nice enough to send me home with some native plant seeds. My father and I are actually growing a native plant garden at our house. We're at the other end of the peninsula, you know, the San Pedro end. And it's about 1.5 years old now, and we're already seeing all these pollinators, you know, local pollinators as things are blooming. And yeah, so it's really lovely. And so I'm excited to hear that you're doing some native planting here as well, particularly as I'm outside, or we are outside the range of the El Segundo blue butterfly, whereas you are very solidly in its path. It's this endangered blue butterfly. But unlike the Palos Verdes blue, which we've been sure to plant stuff for, is all but gone from the wild and they're trying to reintroduce, the El Segundo is still cruising around here. And I actually, on the property even? Oh, that's lovely. I went, there was a conservancy event, we went and saw some. And the tiny little, you know, beautiful blue butterflies, and they're just delightful, yeah. And so, it's I never would have seen them if it weren't for the naturalist there, because I was picturing like a big monarch. Yeah, and they're these delicate little blue things, but they're so lovely, yeah. And they're all, you know, along here, and a lot of their habitat is gone now. And it's kind of exciting. I'll leave you with a thought of, it's cool that you have this big sort of bowl in here. I was over winter break, privileges of being a teacher, right, as I get breaks. And so I figured I should go to Hawaii for my winter break. And I was, yeah, no regrets. And I was in Kauai at this lovely nature preserve where they're trying to bring back some of these endangered native plants to Hawaii. And they were talking about pre-European arrival in Hawaii, the land was divvied up. These different communities would each have almost like a pie slice of the island. And so every group would have all the different parts of the island. You'd have some beach and some lowlands and some highlands. And, you know, it's different plants that grow there and different water levels. Some is good for farming, some's good for gathering different things. And they had actually one of the oldest ones that stuck around even after European arrival. One of the oldest of these systems that continue to be used was in this remote corner of Kauai. And they managed to acquire that land intact. And they have this whole watershed as a result. And they've been able to build a fence and, you know, keep all of these like invasive goats out on either side. And they have one whole watershed, you know, where none of the water all falls in their land, and everything that isn't their land, that water drains other places. So they really have the whole, you know, from the highlands all the way to the ocean. And exactly. And so it's kind of cool looking at yours. You have a little mini version of that same thing. You own this bowl from the top to the bottom and from these bounding sort of ridges on either side. So it's neat to think you have your own little watershed here. And so anyway, I hope you do some more with that. And there's even some of the things I wistfully looked at when I looked up native plants are river kind of side plants. And I said, too dry where we are. And so even having your own little channel, there's even some neat, you know, native willows and other things like that don't grow in the drier places. So exactly, so there's all kinds of neat stream native plants too anyway. So, and they tie in interesting ways. You know, the plants have evolved to be ideally suited for the soil that comes out of some of these rocks that we've talked about, you know, and then feed back into it in these ways. And so anyway, so that's the peninsula. Thanks so much. And I've got some rocks and maps and even like a few slides of some things if you'd like to see them.
Okay.
Is all a result
Yeah.
of landslides, or ocean has claimed part of it?
It's a landslide here, and so all of this has slid down. The waves never came up this far. But when what was in this bowl slid down, it didn't disappear. It slid down there to the coast, and then the waves removed that. So all this material has been removed by waves, but not directly. You know, it all fell down, and then the waves could sort of carry it away.
One day all of this bluff will be taken over by ocean. Is that going to happen?
How high is this?
We're pretty high. We're at like 200-300 feet.
I think you're, so, you know, I mean, you're good. We're looking at about 3 feet of sea level rise by the end of the century. If all of the ice melts, we're kind of right on the cusp. The peninsula in its entirety won't go underwater. It'll become an island. Once again, it used to be a channel island, so, you know, going back to its basics. I measured, and at least a few years ago when I used the best estimate, we would be, I think, 3 or 4 houses up from the new beach. So yeah, I'm not sure. You would be a lot closer in any case. We could check, but yeah, it would be a while for that. Yeah. Well, I won't talk at you too much longer because it might be more fun to have a snack and look at. I brought a couple of maps. Here's General Peninsula one. Here's one that shows all those marine terraces I mentioned, as well as some landslides, and I got a few rocks. But so I'll say just a few more things. And if you want to talk about any of these slides in more depth too, feel free. We can chat about any of these. But so just a few things. So people have been geologizing around here for a long time. This is actually a sketch of part of Catalina. This is 2 harbors at Catalina from a geologic report published in 1897. And so this year marks 125 years of professional geologic studies of our kind of area around here. And I mentioned how faults, they make a bend. So here's the San Andreas Fault, is this black fault here. And you can see it's going sort of straight, and then it curves and it bends along here, and then it straightens out again. And so this whole segment, it's called the Big Bend. And all along that bend, the 2 slides can't just slide past one another. They're bumping into one another as they do.
Whatever
Oh, subduction, yeah, it's not, it's the same kind of idea. It's not to that full extent where a whole plate sinks down, but they crumple together. It's almost sort of like a little mini Himalaya almost, where the two parts sort of crumple together and neither one really is sinking under the other. So you just get so much crumpling. And that's why here's the San Gabriel Mountains, here are the San Bernardino Mountains. That's all along the extent of that bend. And once you get out of that bend, no more big mountains of that extent. Yeah. Yeah, right? And so here we are on the peninsula, and here's an aerial photo. Here's the San Gabriel Mountains, the mighty San Gabriel. See how straight the edge of the mountains are? That's the San Andreas. And so here's our little Palos Verdes fault is out here offshore and then bends around right here, and that's why we get PV. And you see similar things give you some of these hills out here. And Catalina actually is the same thing too. Fault comes and then sort of bends around this way and then straightens out again, pushes up Catalina. And you can see actually all these lighter colored things are faults too. So here's our PV fault stepping around. See this fault comes here and then bends left and straightens out. It's actually quite a bend, and so Catalina is really rugged. There's almost no bend here on this fault that's pushed San Clemente Island up, and San Clemente Island is much flatter in terms of the topography than Catalina. And here's a recent study that highlights this fault and shows you the offshore part. So here's PV Peninsula, here's our PV fault, and then you can see it curving, straightening out, and you can trace it. Then there's these subsea features like Lassa Knoll here. And you can follow that fault parallel to the San Andreas for quite a ways. And so that's ultimately why we have our peninsula. And here's a neat image that shows the underwater topography. So here's PV Hills, but really this whole dashed area is part of this uplift and this anticline folding. And a lot of it is still underwater, but that makes a lot of this shallow water. And we have this big San Pedro Shelf, for instance, a little below sea level today, at least, but way higher than this deep ocean channel between us and Catalina, because this is all pushed up. And you can see the PV fault and this sort of canyon or scarp that is left here, and then it comes up on land here. And you can also see, you're right up at this corner, you're right about where this deep Redondo Canyon is. Right here, and which is where I was just talking to someone about how sand drifts south along the beach, and at Marina del Rey they actually have to pump it so it doesn't drift across the entrance to the marina. A lot of that sand ultimately goes down this canyon, Redondo Canyon, which is part of the reason then why a lot of PV has this sort of sand poor, bouldery kind of beach, is the sand that's moving along goes down this canyon and doesn't drift down and blanket our beaches here. Okay. And then and then I think I won't say much about this, but just the Catalina schist, which I brought a few pieces of. It's this old ocean that was actually being pushed under, or the term is like subducted, beneath North America about 60 million years ago. So about 60 million years ago, the Sierra Nevada were still active volcanoes, and there was the ocean. The Pacific, as big as it is now, used to be even bigger, and some of the Pacific that used to be out there is underneath North America now, was pushed under. And the Catalina schist was a bit of basalt, like in Hawaii or like on some of our headlands, but that was pushed down, subducted down beneath this part of North America. And as it got pushed down, it got under a lot of pressure and a lot of heat, and so it changes. It's a process called metamorphism, where a rock, the minerals in it, without ever melting, the minerals will recrystallize into new, different minerals. And actually, metamorphic minerals are some of the most colorful minerals. So we've got a blue schist, and a green schist, and a black schist, or an amphibolite. And all three of these were the exact same rock at one point in time. And it's just different amounts of heat have determined what new minerals form. And those minerals have different colors. It's sort of interesting, too. In this case, you had cold ocean floor being pushed down against this hot, deep part of North America. So usually the deeper into the earth you go, the hotter it is and the more metamorphosed things are. In this case, it was kind of the opposite. You took this cold stuff, you pushed it down and kind of flash seared it almost, this heat applied to the top. And so This rock you find here sits on top, like out on Catalina, you'll find this high temperature rock, and then below it, you'll find this medium temperature rock, and then below that, this low temperature rock. And at first people didn't know what to make of it. They thought, has everything been flipped over? You know, why are the high temperature ones on top? And then as people figured out plate tectonics, these processes that push plates around and sink them down, it made sense in terms of that. And there's some details. Even within that, the Catalina schist is very special. Usually when rocks are pushed down, they keep going, and that's all you hear from them. The Catalina schist was this special case that was pushed down at this shallow angle so it could sort of scrape off onto the bottom of North America, so it didn't go to this fate of disappearing into the earth. And then as all those mountain ranges I mentioned rotated around, this is millions of years ago, 18 million years ago, here's all of the Santa Monica's and Santa Ynez mountains blocking your ocean view. And then 12 million years ago, they're rotating out of the way, and here they are now all today, those mountains there. And so as they did that, it opened up this whole space in between, and Catalina Island was basically dragged out, or almost like unsubducted. All this rock was pushed under North America and then sort of dragged back out. And so we can see it today. And you can walk through the whole thing on Catalina and go through each of those types, in turn. And there's the 3 amphibolite green schist, blue schist on Catalina. And this was just a view of as you hike down this trail. If you go from like Airport in the Sky down to Little Harbor, you'll walk through old North America and you'll cross this enormous fault that was the boundary into what was old Pacific Ocean. And then you'll walk down through each type of this schist in turn. Yeah, so if you like to go hike it, I'm happy to share some tips. And mostly what you see on the peninsula is Altamira Shale, which is also full of fossils. Here's some whale fossils, 12 million year old sperm whale fossils that just someone realized back in, I think, 2014 at the Chadwick School, which this is a teacher there. They had this rock that had been out in the garden forever, and someone finally said, that's a whale skull. And it's this priceless whale fossil, I think a species that hadn't been described before. And so that's pretty rare, but you can find them. Actually, April 2nd, a colleague, paleo colleague, and I will be doing a Bluff Cove walk and talking about fossil whales there. And there will be a fossil whale expert from the Natural History Museum joining us.
I don't know when that is.
That's April 2nd at 11 a.m. at Bluff Cove. Yeah, it's just down the way. And I can also, though, I'll be sure to get Dan a flyer if he doesn't have one already, and he could share it around. Yeah. Yeah. And
How unlikely.
and so these are pretty rare but spectacular when you find them. But because this is old ocean floor stuff, there's all kinds of little fossils. It's easy to find if you know what you're looking for. Little like fish scales and bits of plant and stuff buried in that rock. And then some volcanic activity produced basalt at the same time, kind of coming up through conduits and oozing out. And so that's where you get a lot of your headlands. And then your diatomite. And so here's an example. A lot of these photos I'm actually sharing are from Catalina because there's great exposures there. Here's a whole thick cliff that's all that sort of solid, white, crumbly diatomite rock. Basically the same stuff that you have here as the Valmonte diatomite. And here are those diatoms under the microscope, those microscopic little fossils. And so you can see like this is 10 micrometers or 10 thousandths of a millimeter, or 100, let's see, 10,000, that'd be 1% of a millimeter. So, and a millimeter is about a 25th of an inch. So this would be about 1/25,000th of an inch, right? So they're small. And but if you put them under a good microscope, you can see all these tremendous, gorgeous patterns. And you can also maybe see that this is partly hollow now that the thing inside it is dead. So that's all that empty space that leaves the rock kind of lightweight. So anyway, that's a little bit extra there. And so yeah, if you want to come up and see rocks or maps or whatever, or ask me about whatever, feel free. And thanks again for having me.